Hi everyone, welcome to E-Content Development Center, Majlis Arts and Science College, Puramannur. Myself, Shamima Rahmat, Assistant Professor, PG Department of Computer Science. In this video, I will introduce to you the basic concept of finite automata and its classification. After watching this video, you will be able to define finite automata. Also, you will be able to get an overview of different classifications of finite automata, that is DFA, NFA, epsilon NFA, Moore machine and Mealy machine. What is an automata? Automata are abstract machines which follow predetermined sequence of operations automatically. These machines accepts strings as input and either accepts or reject it. There are different automatas and the simplest among them is the finite automata. Finite automata. Finite automata are abstract machines which have a finite number of states. This automata accepts the class of language called regular language. They are mainly used in pattern matching tools like Lex and text processing, etc. And the main feature of finite automata are these machines does not have a memory. The basic components of finite automata are an input tape, a reading head, and a finite control. Input tape is the place where the input string is loaded. Symbols are read by the reading head, one symbol at a time. Finite automata are broadly divided into two: automata without output and finite automata with output. Finite automata without output is further classified into Moore machine and Mealy machine. And finite automata with output is further classified into deterministic finite automata or DFA, non-deterministic finite automata or NFA, and non-deterministic finite automata with epsilon moves or epsilon NFA. Let us look into it in detail. Deterministic finite automata or DFA. DFA is a finite automata in which transitions for all inputs should be clearly defined. Also, in a DFA, for an input symbol, there should be exactly one transition. A DFA can be represented by 5 tuples. That is, a machine M is equal to Q, sigma, delta, Q0 and F, where Q defines the set of states, sigma defines the set of alphabets, delta defines the transition function. For a DFA, the transition function is given as Q cross sigma gives Q. Q0 defines the initial state and F defines the set of final states. Let's consider an example. Construct a DFA for the strings starting with 0, 0, where sigma is given as 0 and 1. For the language of set of all strings starting with 0, 0, the strings will be 0, 0, 0, 0, 1, 0, 0, 0, etc. Here we will start with constructing a DFA with the strings of minimum length, that is 0, 0. Here the Q0 is the initial state and Q2 is the final state, and this DFA accepts the string 0, 0. Considering the input symbol 1 for the states Q0 and Q1, we know the first and second symbol should not be 1. It's an invalid string. So we define a transition from Q0 and Q1 to a new state Q3, which is a trap state. That is, this state will not enter the final state. Finally, defining the transition for the state Q2, we put a loop to the state Q2 itself for the input symbols 0 and 1, so that any number of zeros and ones that comes after the 0, 0 will be accepted as a valid string. So the automata is completed and the machine can be defined as the set of states is given as Q0, Q1, Q2 and Q3, and sigma is given as 0 and 1, and the transition for all the states and for all the inputs is defined as a tabular form. Here Q0 is the initial state and Q2 is the final state. Next is non-deterministic finite automata or NFA. NFA is a finite automata in which for an input symbol there can be more than one transition from a state. NFA is easier to construct when compared to DFA. NFA can be represented by 5 tuples. M is equal to Q, sigma, delta, Q0 and F. Q defines the set of states, sigma defines the set of alphabets, delta defines the transition function for NFA, that is Q cross sigma gives power set of Q, and Q0 defines the initial state and F defines the final state. Let's consider an example. The set of strings starting with 0, 0 where sigma is equal to 0 and 1. The set of strings of this language will be 0, 0, 0, 0, 1, 0, 0, 0, etc. Now constructing the NFA is much easier. Here 3 states are there, Q0, Q1 and Q2, where Q0 is the initial state and Q2 is the final state. Here it is not necessary to define all the transitions for all the states. So we can ignore the transition of Q0 and Q1 when the input symbol is 1. So the machine will be defined as the set of states will be Q0, Q1 and Q2, sigma is 0 and 1, and the transition is given in the tabular form where all the transitions are not defined. Q0 is the initial state and Q2 is the final state. Some points to be noted are every DFA is an NFA, and for every NFA there is an equivalent DFA, and therefore NFA and DFA are equivalent since the conversion from NFA to DFA and DFA to NFA is possible, and the set of languages that is accepted by NFA or DFA is called the regular language. The next classification of finite automata is the non-deterministic finite automata with epsilon transitions or epsilon NFA. We can extend NFA by introducing epsilon moves that allows the machine to make transition on receiving empty input. There would be an edge labeled between 2 states which allow transition from one state to another even without receiving an input symbol. This is another mechanism that allows an NFA to be in multiple states at once. Epsilon NFA is given by 5 tuples. M is equal to Q, sigma, delta, Q0 and F. Q is the set of states, sigma is the input alphabets, delta is the transition function, and the transition function for epsilon NFA is given by Q cross sigma union epsilon gives the power set of Q. Q0 is the initial state and F is the set of final states. Consider the example. Here the transition from Q0 to Q1 is possible even without an input, that is 0 or 1, and it is possible with the epsilon move. Next is the classification of finite automata with output, that is the transducers. The first among that is the Moore machine. Moore machine is a finite state machine which has an output value. The output value of a Moore machine is determined by its current state. Moore machine is represented by 6 tuples, that is M is equal to Q, sigma, delta, Q0, delta and lambda. Q defines the set of states, sigma defines the set of alphabets, delta defines the transition function. The transition function for Moore machine is Q cross sigma gives Q. Q0 defines the initial state, delta defines the output alphabet, lambda defines the output function which maps to Q cross sigma gives delta. Here is an example of Moore machine. Here the output of each state is represented with the state names separated by a slash. The length of the output for a Moore machine is always greater than the length of the input by 1. The next machine that comes under the classification of finite automata with output is the Mealy machine. Mealy machine is a finite state machine which has an output value, and the output value of a Mealy machine is determined by its current state and current input. The Mealy machine is represented by 6 tuples, that is M is equal to Q, sigma, delta, Q0, lambda and delta. Here Q is the set of states, sigma is the input alphabets, delta is the transition function which is given as Q cross sigma gives Q, Q0 is the initial state, delta is the output alphabets, lambda is the output function which is given as Q cross sigma gives delta. Here is an example of Mealy machine. In a Mealy machine, the output is defined with each transition along with the input symbol separated by a slash, and the length of the output of a Mealy machine will be always equal to the length of the input. This is all about the classification of finite automata. By this, I conclude this session. Hope you all understand this topic. Thank you for watching this video.